Alrighty, the topic of this video is something like counting the number of atoms or ions contained within a unit cell, the smallest repeating unit in a salt. Yeah, it's kind of a three-dimensional thinking game where I'm trying to imagine how many of these 1, 2, 3, 4, 5, 6, 7, 8, what fraction of each of these 8 individual atoms or ions in this, what we call the unit cell, the smallest repeating unit, contribute only to one particular unit? Well, I don't know. Is the answer given? It is. Don't look at that. All right. If I think about this atom as sitting at the corner of 1, 2, 3, 4, 5, 6, 7, 8 blocks, unit cells, then perhaps you can imagine that 1/8 of this sphere is dedicated to the red box, but 1/8 is dedicated to the top left box, 1/8 is dedicated to the top back box, top back left, and one to the top back right, one to the lower right rear, lower left rear, lower left front, and lower right front. So that's 8 boxes, and 1/8 of each of those atoms or ions is dedicated to that unit, to that unit cell. That's the ions on the edges. But there are sometimes ions or atoms in the center of a box, or the center of a unit cell. In that case, if it's absolutely in the center, then that entire golden colored atom in this cartoon counts as dedicated to that particular unit cell. This one's called the body center cubic because it has an entire atom or ion inside the body of the cell. Another possibility is that the atom or ion is on the face of a cube, or the face of the unit cell, therefore called face center cubic. How much of this atom or ion, how much of this one, 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 if they're all 6 of them on the faces, how much of this is dedicated to this box? Can you imagine? Isn't there another box to the right of this, or another box to the left of this, or another box above this one, another box below this one, another box outcoming towards us for this one? And so the answer is half of it. Half of this one, 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 half of this one are dedicated to this unit cell. Interesting. There we go. Another cartoon. So half of it to this one, half of it to that one for the faced atoms or ions. Another possibility is, what if the atom or ion's on the edge? Oh, goodness gracious. Yeah. It says how much would an atom or ion in a cubic unit cell at a position shown on the edge, how many other boxes does this atom share with? And the answer is 4. There's one up here right above this one. There's one right in front of this one, but there's also one kind of diagonal up and out towards us and up, kind of kitty corner across from this one. Boy, that's kind of hard to see, isn't it? I wish I had a better cartoon for that. Let's try one. Oh, my program's responding slowly to my scrolling. Alright, so I tried to highlight the red ones, red atoms on the face, 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 face. Blue atoms on the corner, 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 and green atoms on the edge, 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 edge. That's a lot of edges. What's the formula for this unit cell? In other words, how many red ones, how many blue ones, how many green ones? Jeopardy music. Pause the video if you'd like to do it. Otherwise, here's the answer. What about the blue ones? The blue ones are easy, yeah? 1/8 of this blue one counts toward the cell because it's on the corner. 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8. So I think 8 times 1/8 is 1. So the blue ones contribute 1 to this unit cell. What about the faces? I have 1 half, 1 half, 1 half, 1 half, 1 half, 1 half. Doesn't that add up to 3? 3 red ones contributing to this unit cell? I believe so. What about the edges? The edges contribute 1/4. 1/4, 1/4, 1/4, 1/4, 1/4, 1/4, 1/4, 1/4, 1/4, 1/4, 1/4, 1/4. What does that add up to? 1/4 and 1/4 and 1/4 and 1/4 adds up to 1. 1, 2, 3, 4 adds up to 1, and 1, 2, 3, 4 adds up to another one. How about 3 green ones as well? I think I got this formula. Well, I guess I would really write it, oh, fiddlesticks. That's not for this question. Alright, fine, be that way. Well, it's still valid. If all of the atoms were the same, then I counted 3 of the red ones, 3, no, yeah, right, yeah, no, 1, 2, yeah, 3 red ones, 3 green ones, and 1 blue one. But I suppose if they were all the same, it would be a total of 7 particles to that unit cell. But as I've tried to hint here, perhaps they're different. So the formula for this would be red 3, blue 1, green 3. Interesting. Whatever the red, blue, and green atoms or ions were. Here's a super tricky one. This will freak you out. Here's a ceramic type salt crystal unit cell. It has yttrium in blue, barium in green, copper in kind of an orangish color, and oxygen, as usual, in red. Looks like the oxygens are mostly on the faces. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oxygens on the faces. I've got 2 oxygens, though, totally within the cell. 1, 2. I've got coppers in the middle of the cell. 1, 2, 3. Oh, shoot, told you an answer. And barium, I've got 2 on 4 edges. 2 bariums, 2 bariums, 2 bariums, and 2 bariums. And yttrium, only 1 at each corner. Yttrium, 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 yttrium. That's a tongue twister if you say it too fast. Pause the video. What's the formula for this? It's actually a superconductor. Cool demonstration in class. I can't hum. Do you watch Jeopardy ever? I don't, but I used to. I mean, I've seen it before when I was a way young boy. Anyways, I was bored. It's a smart show, though. Alright, the answer is, I count, 1 yttrium total, 1/8 of each of these 8 for the box. 1/4 barium, 1/4 barium, 1/4 barium, 1/4 barium. That's 1 barium. Similarly up here, 2 bariums. 2 bariums? 2 bariums. Copper, if copper's totally in the middle of the cell, 1, 2, 3 coppers. 3 coppers, 3 coppers. And I count 1, 2 oxygens totally inside the cell, and half and half make one, and half make another one. Half and half make one, and half make another one. Wait, so there's half and half is 1, half and half is 2, half and half is 3, half and half is 4, 5, 6. 6? Oh, and half is 7. Phew, got it right. Here's some other cool views of these unit cells, a complicated repeating unit. Hard to believe, but from here we can go further, but we usually don't, but it's possible to say, if you know the size of the cube and you know the density of the stuff, you can actually use a little bit just of simple geometry and knowledge of what density is to say, well, what if my cube was 4.95 angstroms on the side? I could get the volume of that cube. If I knew the volume of the cube, I could rearrange, if I knew the density, to get the grams per unit cell. And if I took that further to say if 1 unit cell had 4 atoms in it, what must be the mass for a mole of those atoms? And it comes out to 207 in this calculation. I'll let you stumble through the unit conversions. It's all straightforward. We've seen it before in terms of density, mass, volume, length times width times height, and number of particles in a mole. And But I don't think I will torture you with one of those on a test, but if I did, I'd make sure to give you another practice, perhaps in lecture. Thanks, guys. Take care. See you soon.